Good day everyone. Today for CAB401 High Performance Parallel Computing, I'm going to present to you the Apache STORM Framework. So what is Apache STORM? Apache STORM was originally created by Nathan Mars and the team at Backtide. Its initial release date was on the 17th of September 2011. It had its last stable release, version 2.2.0, released on the 30th of June 2020, and whereby it works in a majority of programming languages. It is written in primarily the Clojure and Java programming languages. However, for the purpose of this demonstration, you are going to see a application of the Apache STORM framework presented to you in the Java programming language. So what is Apache STORM? Apache STORM is fault tolerant, flexible, reliable, and supports any programming language. It allows for real-time stream processing. In addition, STORM is unbelievably fast because it has an enormous amount of power when it comes to processing data. STORM can keep up its performance even under increasing load by adding resources linearly. Now, as you can see from the picture on the left, the STORM topology is made up of primarily two components, which you will see mentioned a lot throughout this presentation. We have spouts on the left and bolts on the right, with data streams flowing between the spouts and bolts. From slides 4 down to 6, I have provided a complete setup process for Apache STORM locally. Now do bear in mind that this is for Mac users. However, it works on both those who own a Mac with the M1 system on chip, as well as those who own the older generation Macs which run on the Intel based chips. So feel free to download a copy of these slides, which will be linked in the video description, and read through the guide when setting up the Apache STORM integrated development environment on your local machine. Down to the STORM architecture. So firstly, I'm going to explain to you the STORM topology. So as I mentioned earlier, the STORM topology is made up of spouts, bolts, and the main topology itself. So let's start with the most basic category, the spouts. A spout is a stream source for bolts. It reads data from different data sources and emits a tuple as its output. A spout can further be categorized into two main categories: a reliable spout and an unreliable spout. A reliable spout replays a tuple if it is not processed by any bolt, and an unreliable spout does not replay a tuple if it is not processed by any bolt. The next component in a STORM topology is the bolt. A bolt processes the tuple emitted by a spout. There can be multiple bolts in a topology that can be used to either perform sequential or parallel execution of tuples. Bolts can be used to perform tasks such as filtering, aggregation, joins, etc. A complete operation like processing data from Twitter, for example, may require multiple bolts that will execute sequentially for performing operations like filtering relevant tweets, aggregating the hashtags, and then writing it to a file as an output. From slides 9 to 11, for those of you who are going to download this copy of the PowerPoint presentation onto your local machine and read along with me, I have outlined several organizations to date that utilize Apache STORM and some of its use cases. I won't have the time to go through all this, so I'm going to pick two organizations, and I'm going to start with the Weather Channel. So at the Weather Channel, several STORM topologies are used to ingest and persist weather data. Each topology is responsible for fetching one dataset from an internal or external network, i.e. the internet, reshaping the records for use within the company, and persisting the records to relational databases. It is particularly useful to have an automatic mechanism for repeating attempts to download and manipulate the data when there is a hiccup. The next most common organization that utilizes STORM is Twitter. STORM powers a wide variety of Twitter systems, ranging in applications from discovery, real-time analytics, personalization, search, revenue optimization, and many more. STORM integrates with the rest of Twitter's infrastructure, including its existing database systems such as Cassandra, Memcached, etc., the messaging infrastructure, mesos, and the monitoring or alerting system. Storm's isolation scheduler makes it easy to use the same cluster for both for production applications and in development applications. And it provides a sane way to do capacity planning. So here we are looking at a mock-up of what it's like to have a single worker node in an Apache Storm cluster or topology, right? And down here we're going to see a graph showing the speed up of a single worker node. On the left you're going to have the Storm latency in version 2.0 versus version 1.2.2 of a single worker node. And on the right, you're going to have a graph that shows the CPU versus throughput of a single worker node in both version 2.0 versus version 1.2.2. On to slide 14 here, we can see a speed up using the Apache Storm cluster or framework with 2 worker nodes. I have outlined in the diagram what a single worker node looks like and what 2 worker nodes looks like. And down on slide 15, you can observe that we have the Storm latency in version 2.0 versus version 1.2.2 of 2 worker nodes. And on the right, we can see a CPU versus throughput graph of 2 worker nodes in version 2.0 versus version 1.2.2. Now, for the actual demonstration of the Apache Storm framework, I have parallelized matrix multiply, or in other words, the hello world of parallel computing. So here, I've taken a screenshot of the output for the program I've written, and sequentially it was run in Java. So as you can see, the processing time for this program to run sequentially was 0.0001803 seconds, or 1.803 times 10 to the negative 4 seconds. I've even outlined in the screenshot when the sequential process begins and when it ends. The time that I have converted here into seconds is essentially this time up here in nanoseconds, and I've just put it through a converter and obtained the answer in seconds. For the parallel side of it, I couldn't include the processing output because the file was too large to fit on this slide, but what I have done is I've converted the time and then I've divided it by the time taken to run the program sequentially and obtained a percentage increase. So as you can see, the processing time for the program to be executed parallel was 0.3084932 seconds, which is approximately 3.084932 times 10 to the negative 2 seconds. This is approximately, if you take the parallel output processing time divided by the sequential output processing time, multiply that by 100%, will give you an approximate 17.1% increase in the processing time of the program as compared to when the program is run sequentially. Here I've given you an overview of the data spout, or how I've coded it up in my preferred IDE, which is IntelliJ IDEA. So this is an overview of the data spout. I've split it over multiple slides because it was too large a code block to fit into one slide. So this is another overview of the data spout. Down to this section here, which is an overview of the multiplier bolt. And then finally an overview of the main topology. And there, another overview of the main topology as well. Now down to Storm's top 10 alternatives. This is going to form the critique section of my PowerPoint presentation. So as you can see, I've included 10 alternatives to Apache Storm and some of the end user reviews for each of the solutions I've provided. So let's go through some of it. So the first would be Microsoft SQL, second Google BigQuery, third would be Snowflake, fourth would be Kubel, fifth would be Google Cloud Dataflow, sixth would be Amazon EMR, 7 would be Cloudera, 8 would be Timmy Suite, 9 would be Dreamio, and 10 would be Databricks. Now as you can see, most of them are more usable, with some of them being better at support and a handful of them being easier to set up compared to Apache Storm. Now down here we can see the Apache Storm market share versus other big competitors. Now it is observed from the graph in the big data category that Apache Storm has a market share of approximately 0.52%. As you can see from the graph, Snowplow dominates the market with 61.15%, followed by Informatica 9.97%, and finally Apache Hadoop, which consumes about 7.75%. Onwards, we can see some of the industries that use Apache Storm today. This research was all relevant, so it was all published about 3 to 4 months ago. So as you can see, for the industries of computer software, we have approximately 824 companies that utilize Apache Storm, whereas for the industry of information technology and services, we have about 310 companies that utilize Apache Storm. Down to the countries that utilize Apache Storm, now we have 2 main countries that use Apache Storm. We can see the United States with approximately 1,473 companies in the United States still utilizing Apache Storm to date, and approximately 140 companies using Apache Storm in India as well.